Here we're going to talk about a one-way ANOVA. And I'm not going to go into the details about the one-way ANOVA. You can read through that in your chapter. I just want to take you through of how you would do the calculations for a one-way ANOVA. And so for this example, what we have are 3 treatment groups for depression. And so we've got 6 people randomly assigned to get Prozac, 6, and these would all be moderately depressed individuals, 6 to get cognitive behavioral therapy, and 6 to get a placebo. And so you'll see we got our summary data for each of these. If you add these up, the T means just the total for a particular category, for a particular group. So this adds up to be 30. 30 divided by 6 would give us a mean of 5. And then here's our sum of squares for this set of data. And then for the therapy condition, same thing for our summary data and summary data for a placebo group. So just ahead of time, in advance, we already see the placebo group for this. By the way, the scores then is if we put them in groups and randomly assign them to the different treatment conditions, and let's say 2 months later we look to see, give them maybe a back depression inventory, and we see their scores, and here's their scores. So a lower score means less depressed. And you'll see our cognitive behavioral therapy group had the lowest depression mean, next to the Prozac group, and next to the placebo group. What we don't know is we don't know if those differences are larger than what we'd expect to occur just by chance. And the advantage of the one-way ANOVA over the independent measures t-test is if we have more than 2 groups, we can look at them, look at all those groups at the same time to see what the effect is. It's what we call the omnibus ANOVA. So our first step is to figure out the total sum of squares, just like what we would do in when we normally figure out our sum of squares. So what we're going to do, we're going to get all the x's, square them, and then add all those up. And when you do, so again, that would be like 36 plus 16 plus 25 plus 9 plus 16 plus 64 plus 16, and so on, all through all 18 scores. When you do that, the x squared equals 542. So we have 542 minus, and then this g is just the grand total. Okay, if we add up all the scores together, what does it add up to be? So g equals 90, right? Because our total here is 30 plus 18 is 48 plus 42 equals 90. So 90 squared divided by our sample size, which is 6 plus 6 plus 6, 18. And so this is 542 minus 8100 divided by 18, which is 542 minus 450 equals 92. So the total sum of squares in this whole data set is 92. From here, we're going to break that out into what we call the between treatments, okay, the variability that exists between these groups, these 3 groups, and the within subjects variability, which means all of them, the variability that exists within each of these groups, okay? So we've got our first step. We've got our total sum of squares, which is 92. Next, we want to figure out the within treatments sum of squares. Okay, sum of squares within. Quite easy to do, especially with how we've been given the information here. We're just adding up all the sum of squares within each group. So all this is 16 plus 4 plus 24 equals 44. So our sum of squares within equals 44. Next, we want to figure out our sum of squares for the between treatments. There's 2 ways we can do this. We can do this the easy way or the more laborious way, and I'll do both of them for you. So one way is to just say, well, if we know that our sum of squares between and our sum of squares within has to add up to be our total, we can just take a total that we figured out, which was 92, minus the within that we calculated, which was 44. And that would give us our are between. So 48. Okay. The other way in which you can do this, and I just want to show you so you see how it is that we would get it, and that we can double check this particular answer to make sure these two calculations are correct, is we can use this formula here. So basically what we're doing with this formula is we're taking our totals, a total within this group, squaring it, and dividing it by the sample size within that group. Okay? So to write out this formula, what we're doing is 30 squared divided by 6, right? Because it took 6 numbers to get that 30, plus 18 squared divided by 6, plus 42 squared divided by 6. And we're going to add those up, and then what we'll subtract out is this g squared divided by 10, by the sample size, the total sample size. We figured this out one time already in our first one as we went through. We figured out g squared divided by 10, that was 450. So we're going to subtract 450 out of this. Okay, so for this first up here, 30 squared divided by 6 gives us 150, plus 18 squared divided by 6 gives us 54, plus 42 squared divided by 6 gives us 294. Okay. We add those up, 150 plus 54 plus 294, 498. We have 498 here minus 450, and that equals 48, just like we got up here. Okay, so now we've got our sum of squares. We've got our sum of squares between total. We've got our sum of squares within. We've got our sum of squares between. We need to figure out the degrees of freedom for each of these categories. So our total degrees of freedom, we have 18 subjects minus 1 gives us 17. For our between is just K just means the number of groups that you have, the number of treatments that we have. We have 3 minus 1 gives us 2. And then our degrees of freedom within, there's 2 ways we can figure it out. We can either just say take the total minus the between, which would give us 15. The other way is for each of these groups, we look at this, we've got 6 subjects, we figure out the degrees of freedom in each group. 6 subjects minus 1 gives us 5. 6 subjects minus 1 gives us 5. We're figuring out the degrees of freedom within each category. 5. 5 plus 5 plus 5 is 15. Okay? Got the same thing either way. Gives us the same answer. Okay? So we got our degrees of freedom now. And then what I want to do next is put this in for you into an Anova table. So these are the summary tables that we use for Anovas. So you notice we got our source of the variability here. We've got our sum of squares here, degrees of freedom, and then the mean square. And if you remember from the chapter 4, mean square is just another way of saying variance, and that's what we're doing here, analysis of variance. So we'll figure out the mean square, and the formula for a mean square for the variance you learned in chapter 4. Mean squared equals the sum of squares divided by the degrees of freedom. And then we've got the F ratio that we're figuring out. Okay, so our between treatments sum of squares that we figured out was 48. Our within that we figured out was 44. And our total that we figured out was 92. Degrees of freedom for between treatments we figured out to be 2. Within treatments was 15. And our total was 17. And so now to get this mean squared, I'm going across the row this way. 48 divided by 2 gives me 24. Here, 44 divided by 15 gives me 2.93. Alright? So I've got the mean squares for each, the F ratio, just equals the mean square between divided by the mean square for within. Okay? 24 divided by 2.93 equals 8.19. Okay? So we've got our F ratio here, we've got our mean squares, we got everything within this Anova table. What we want to figure out, just like we always want to do, is this larger than what we'd expect by chance. The F ratio, F distribution looks something like this. Remember, we're looking at squared differences, so we're not going to get any negative numbers here for this F distribution. And now we need to look this up in the back of the book, in the table. The F distribution table begins on page 590. You'll notice here with the F distribution, we've got up here the degrees of freedom in the numerator. That's the numerator of the F ratio. Degrees of freedom in the denominator of the F ratio. So for ours, the degrees of freedom in the this is our numerator of the F ratio. The degrees of freedom that corresponds to that is 2. Degrees of freedom that corresponds to the denominator, this is the denominator, is 15. So 2 and 15 are degrees of freedom. 2, and down here is 15. Okay. Now you notice we've got two different numbers here. We've got one in normal type and one in bold type. The one in normal type is for an alpha of 0.05. The number in bold type is for alpha of 0.01. So if we set alpha at 0.05, remember we can't do two-tailed tests with this. Because it's always one-tailed because there's no negative numbers on here. Okay, so our cutoff would be 3.68. Our F ratio 8.19 out in here, certainly in the critical region. Here's another example where we would reject the null hypothesis. So we're rejecting the null hypothesis, and what does that mean at this point? All that means, all we can say is we know that at least one of these mean differences is significantly different from one of the others. One of the means is significantly different from the other. So really, logically, as we look through this, the biggest mean difference is between the cognitive behavioral therapy group and the placebo group. So in essence, there must be a significant difference between those two groups. But what we don't know right now is there a significant difference between Prozac and cognitive behavioral therapy? And is there a significant difference between placebo and Prozac? Okay, that's what we'll get into in just a little bit in another session. We're looking at post hoc tests.